something is amiss in our comprehension of the cosmos. Cosmology is approaching a critical juncture, grappling with one of its most fundamental issues: how quickly is the universe expanding? For over 10 years, two different measurement methods have been at odds. Observations of the present-day universe typically show that the rate of expansion, known as the Hubble constant, is about 9% faster than what is predicted based on data from the early universe. Researchers had hoped that the James Webb Space Telescope, the most advanced telescope ever created, would help resolve this issue definitively. However, consensus has yet to emerge, as the telescope's remarkable new observations have further solidified the discrepancy, posing a potential challenge to the established cosmological model. Now, the need for new physics to either modify or entirely replace the 40-year-old theory is under serious debate. A thrilling and intriguing possibility is that we are overlooking some aspect of the universe. Join us as we delve into how the new ultra-deep images from James Webb have just confirmed that there is something seriously flawed in our understanding of the universe. Our universe began with an explosion, the Big Bang. Energy, mass, and space appeared almost instantaneously. From there, the young cosmos formed a growing plasma mixture of matter and antimatter particles that materialized and annihilated one another as they collided. Left unchecked, the matter and antimatter in this plasma would have destroyed each other entirely. However, scientists believe an unknown imbalance allowed more matter to form than antimatter, thus saving the universe from immediate annihilation. Gravity then compressed this plasma, heating the matter to such an extent that sound waves, known as baryon acoustic oscillations, traveled through the medium at slightly more than half the speed of light. At the same time, the dense energy content of the early universe stretched spacetime, pushing a small portion of matter safely away from the heat. As the universe expanded like a balloon, the standard narrative suggests that ordinary matter, which interacts with light, began to clump around invisible dark matter, forming the first galaxies connected by a vast cosmic web. As the universe's contents began to spread, its energy density, and by extension, its rate of expansion, diminished. Yet, around 5 billion years ago, galaxies began receding faster, driven by the mysterious force known as dark energy. The most straightforward and widely accepted explanation for dark energy is that it functions as a cosmological constant, a uniform force that remains constant across both space and time, woven into the fabric of expanding spacetime. Named lambda by Einstein in his theory of general relativity, dark energy density stays the same as the universe grows, while the density of ordinary matter drops. Eventually, dark energy became the dominant contributor to the universe's expansion. When combined with ordinary matter and dark matter, the energy densities of each set an upper limit on the universe's expansion speed. These elements form the core of the lambda cold dark matter, lambda CDM model, which describes the evolution of the universe and predicts its eventual fate, a heat death known as the Big Freeze. Many of this model's predictions have been proven highly accurate. However, this is where the trouble begins. Despite extensive research, astronomers are still clueless about the true nature of dark matter and dark energy. As Fova, an astronomy professor at University College London involved in dark energy galaxy surveys, states, "Most scientists agree that the universe's current makeup is about 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing reality is that we still don't understand the latter two. An even greater challenge to the lambda CDM model, however, is the growing issue known as the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. The disparity is so significant that it has become a pressing problem in cosmology. Measurements made from observing the early universe suggest it is expanding far faster than predicted by the lambda CDM model. These methods have undergone extensive testing and validation through numerous observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team responsible for the latest James Webb measurement, put it, "The only explanation for the discrepancy between the two approaches is that our current model is likely missing something." Measuring the universe's expansion involves more than just using a radar gun. One of the primary methods to assess this rate examines the cosmic microwave background, CMB, the universe's first light emitted about 380,000 years after the Big Bang. This imprint is observable across the entire sky and has been mapped to derive the Hubble constant, with less than 1% uncertainty. Between 2009 and 2013, the European Space Agency's Planck satellite produced a detailed map of the CMB. In this cosmic snapshot, the universe is nearly uniform, but slight variations in temperature, where matter is denser or sparser, mark the locations where baryon acoustic oscillations left their imprint. This soap bubble structure expanded into the cosmic web, a network of strands linking galaxies at their intersections. By studying these ripples, cosmologists inferred the quantities of regular matter, dark matter, and the cosmological constant, or dark energy, and calculated the Hubble constant, which came out to roughly 67 kilometers per second per megaparsec. Let's take a moment to break down this number. If a galaxy is 1 megaparsec away, it will recede at a speed of 67 kilometers per second. At a distance of 20 megaparsecs, this recession grows to 1,340 kilometers per second, continuing to accelerate as distance increases. If a galaxy is farther than 4,175 megaparsecs away, it will recede faster than the speed of light. Another method to measure this expansion rate involves using Cepheid variables, pulsating stars whose outer layers expand and contract as they absorb and release radiation, causing them to flicker in a predictable pattern. This behavior, discovered in 1912 by astronomer Henrietta Swan Leavitt, allows astronomers to determine the absolute brightness of these stars, which can then be used to estimate their distance. The Cepheid-based technique, known as the cosmic distance ladder, was a groundbreaking discovery that allowed astronomers to measure vast distances. The first rung of the ladder is constructed by measuring nearby Cepheids and cross-checking their distances. Following this, the distances of more distant stars and supernovas are determined by observing how much their light has been stretched or redshifted as the universe expands. By comparing this data, astronomers can calculate the Hubble constant. In 2019, Adam Rees and his team utilized this method by pointing the Hubble Space Telescope at the Milky Way's nearest neighbor, the Large Magellanic Cloud. Their results were explosive, indicating a much higher expansion rate of 74 kilometers per second per megaparsec when compared to the Planck measurements. However, Hubble's results were limited by its lack of precision in crowded regions of space, which caused distance cues to blur with neighboring stars. Some dissenting cosmologists argued that this discrepancy might have been due to a measurement error, but when the James Webb Space Telescope, JWST, launched in December 2021, it was expected to resolve or perhaps confirm this discrepancy. With its 6.5-meter wide mirror, almost 3 times the size of Hubble's, and its superior infrared capabilities, JWST was able to observe fainter objects and detect a wider range of wavelengths. In a study comparing Cepheids in the galaxy NGC 4258 to supernovae, Rees and his team found results nearly identical to their previous work, 73 kilometers per second per megaparsec. Other measurements, including those by Wendy Friedman with the Hubble Space Telescope and using gravitational lensing, returned similar results, around 69.6 and 66.6 kilometers per second per megaparsec, respectively. The implications of these results have shaken the cosmological community, as cosmologist Roma Call from the University of California, Merced, explains. Even a 7 kilometers per second difference, though small, is extremely unlikely to be a random occurrence given the precision of the measurements. This has sparked a split in the cosmology community, with different factions proposing various explanations. Some suggest measurement errors, while others propose new physics or a combination of both. Call believes that much of the data points toward the need for new physics. The leading hypothesis is that dark energy's behavior has changed over time. If dark energy was once stronger and then gradually faded, it would make the universe appear smaller in its earlier stages, resulting in a faster expansion rate today. Other possibilities include the existence of two types of dark energy or dark matter interacting with light, but these theories introduce complications that many cosmologists are hesitant to embrace without further evidence. JWST's discoveries are not just challenging our understanding of dark energy and dark matter, they are reshaping our ideas about galaxy formation. By looking further back in time than ever before, the telescope has revealed galaxies that were much more massive and advanced than the Standard Model had predicted, forming just 300 million years after the Big Bang. Early galaxies, which should have been composed of young, hot stars, were found to have heavy elements and even supermassive black holes at their cores, features that challenge the traditional model of galaxy evolution. These findings have intensified the debate within cosmology, suggesting that the processes governing galaxy formation may have been more rapid and efficient than previously thought. In addition to addressing these profound mysteries, JWST's findings have also deepened the puzzle surrounding dark matter and dark energy. Despite being the dominant components of the universe, both remain poorly understood. While dark matter interacts gravitationally, its precise nature is still unknown, prompting ongoing research into its detection. Similarly, dark energy is responsible for the accelerated expansion of the universe, but discrepancies such as the Hubble tension raise the possibility that dark energy's properties are not uniform across spacetime. Alternative theories propose dynamic forms of dark energy that could evolve over time, influencing the expansion rate differently at various stages of the universe's history. To solve these mysteries, astronomers will need both advanced observational tools like JWST and theoretical frameworks that can incorporate the new data without discarding the successes of current models. The implications of JWST's discoveries extend far beyond cosmology, influencing broader astrophysical questions, including the origins of life and the conditions necessary for life to arise on other planets. By studying distant galaxies, astronomers hope to uncover clues about how Earth-like planets may form around other stars, offering potential insights into the prevalence and diversity of life in the universe. Looking ahead, JWST promises to continue pushing the boundaries of our cosmic understanding. Its unprecedented sensitivity and resolution will allow astronomers to study the atmospheres of exoplanets, map galaxies in greater detail, and examine the earliest epochs of cosmic history with unparalleled precision. These efforts will not only deepen our understanding of the universe's path, but also pave the way for groundbreaking discoveries that could revolutionize our comprehension of physics, astronomy, and our place in the cosmos. As JWST embarks on its operational phase, astronomers eagerly anticipate the new insights that will emerge, whether unraveling the mysteries of dark matter and dark energy or understanding galaxy formation.